This is the 20th video in a series devoted to ordinary differential equations, and we've been working through using the Laplace transform to solve differential equations, and we're going to look at that a little bit more today with a couple of examples of discontinuous forcing functions. And the first such discontinuous function we'll look at is called the unit step function. So the unit step function, which we'll call u of t, is defined to be 0 when t is less than 0 and 1 when t is bigger than or equal to 0. So it's like a single step that occurs at the y-axis. But it's pretty common to use a shifted version of this function, and that'll be u of t minus t naught, so that's been shifted to the right by t naught units. So that means it's 0 when t is less than t naught and 1 if t is bigger than or equal to t naught. So I've got a picture of that situation here. So notice it's like a single step that is 1 unit high at t naught. Okay, so the first thing that we'd like to do is determine exactly how the unit step function interacts with other functions with respect to the Laplace transform. So let's look at that. We'll do that just via a little bit of exploration. So let's say we're taking the Laplace transform of this shifted unit step function, u of t minus t naught, when it's being multiplied into the function f of t. So how can you maybe think about this u of t minus t naught times f of t? Well, I think maybe a really good way to think about it is that this unit step function is like a switch. And what it does is it's off when t is less than t naught, but it's on when t is bigger than or equal to t naught. And in fact, when it's turned on and multiplied by a function, that tells you that its value is a function value, f of t in this case, everywhere after t naught. So in this case, the picture would look something like this. So there's our t naught. Before we hit t naught, this is like just 0. And then after we hit t naught, it's whatever the value of the function is. So let's say our function looks like that. That's the graph of our function. So we're like turning that function on, if you will. Okay, so let's go through the calculation of this just using the definition of the Laplace transform. So this will give us the integral from 0 up to infinity, and then we'll have e to the minus st times u of t minus t naught times f of t dt. So something like that. But now let's notice that since u of t minus t naught is 0 until we hit t naught, then we probably shouldn't start this integral at 0. In fact, we don't change anything at all if we start this integral at t naught. Because notice, integrating from 0 to t naught will give us a value of 0 by the definition of the unit step function. Okay, and now from here we'll make a change of variables. So I'll use tau for my change of variables. So let's set tau equal to t minus t naught, and let's notice that d tau is just dt. So nothing fancy is going on with that, but something fancy is maybe going on with with the bounds of integration. So let's notice when t is equal to t naught, that means that tau is equal to 0. So that in fact like shifts us back to the origin. Okay, so that means we can rewrite this as the integral from 0 to infinity. We'll have e to the minus s times, well, it won't be t anymore. It'll be something in terms of tau, where we've solved t for tau here. But notice if we solve t for tau over there, we get tau plus t naught. So again, that's just t, and then we'll have u of tau, but we might as well not do u of tau because u of tau is identically equal to 1 for values of tau between 0 and infinity by the definition here. So we don't really need to put that in here, but what we do need to put in here is f evaluated at tau plus t naught. So we'll have something like that. And then from here, what we'll do is take this exponential and see if we can simplify it using exponent rules. This will be equal to e to the minus s t naught and then e to the minus s tau. So this s t naught is a constant with respect to the integral. Let's recall that now this integral is with respect to tau, so that means we can bring it outside the integral. So this will give us e to the minus st naught, and then we'll have the integral from 0 to infinity of e to the minus s tau, and then f of tau plus t naught d tau. But let's notice that what's left over here, this integral, is in fact the Laplace transform of a function. And it's the Laplace transform of a shifted version of our original function f, where we have shifted to the left by t naught units. So we can write this as follows. We'll have e to the minus s t naught, and then we'll have f, and then we'll have the Laplace transform of f at t plus t naught, where I've exchanged t and tau again, just to keep it more in line with what we have right here. Okay, so if we read from the extreme left to the extreme right, we'll see that we've got some sort of shifting action occurring when we include this unit step function. And in fact, we'll do some examples, but as we clear the board for examples, we'll put this new shifting lemma right here. Okay, so now I want to look at two examples of Laplace transforms involving this unit step function. But before I do that, I'd like to recall that on the last board, we derived the following shifting lemma. This is sometimes called the second shifting lemma. And I've rewritten it a little bit, but I think this is a more standard way to see it if you would have seen it in a textbook. So we have the Laplace transform of u of t minus t naught times f of t minus t naught equals e to the minus t naught s times the Laplace transform of f of t. So this condenses all of the shifting over here. But notice if we were to place this t minus t naught here with a t, that would be the same as replacing this t with a t plus t naught. But I'll leave it just like this for consistency across what you might see in a textbook. Okay, so now let's look at this first example. So we've got the Laplace transform of u of t minus 2 times t squared plus 2. So let's start by noticing that this should be equal to e to the minus 2s from this first term here. And then we'll have the Laplace transform of shifted versions of this. So these are set up not like this, but they're set up so that we have to do a little bit of work. And that work will be, like I talked about, replacing t with t plus t naught in both of these. So that means here we'll have t plus 2 quantity squared plus t plus 2. Great. And so notice that if we define our function to be this t plus 2 object, then this function evaluated at t minus 2 will give us exactly this t squared plus t thing. So we're cool there. Okay, so now let's simplify what's going on inside of the parentheses, or maybe expand it all out, I should say. So we have e to the minus 2s, and then we have the Laplace transform of, let's see, it'll be t squared plus 5t. So we get 4t from multiplying t times 2 and then adding it to itself, and then we get another one from the t plus 2. And then finally plus, I believe it will be the number 6. For the same sort of reason. Now we can use our Laplace transform rules for t squared, 5t, and 6, and that'll give us e to the minus 2s out front. And then here we'll have something like 2 factorial, which is just 2 over s to the 2 plus 1, so that's s cubed. And then we'll have 5 over s squared, and then we'll have 6 over s. Again, that's just from standard Laplace transforms like we saw in previous videos. Okay, so let's see what we have here. So let's maybe do this all at once. So we've got the Laplace transform of u of t minus pi times sine. So that's going to be e to the minus pi times s. And then the Laplace transform of sine of t plus pi. So we have something like that going on. But then how can we calculate the Laplace transform of sine of t plus pi? Well, there's actually a sum angle formula. So let's maybe put here that you might want to use a sum angle formula. I'll let you guys look that up, but that should be fairly easy to find on like trig identity Wikipedia. And that says that sine of t plus pi is the same thing as minus sine of t. So we can bring this minus sign out in front of the whole thing, and we'll have minus e to the minus pi s, and then the Laplace transform of plain old sine. But now we can do that. The Laplace transform of plain old sine of t is 1 over s squared plus 1. So that leaves us in the end with minus e to the minus pi s over s squared plus 1. Okay, so now that we've got some practice with this, let's solve some differential equations that involve this unit step function. So now we're going to jump right into solving a differential equation involving the unit step function. You might look at this and say there's no unit step function here, but in fact there is, and it's built in to this piecewise function. So we'll discuss that as we rewrite this. Okay, so what we'll do is first rewrite this involving the unit step function, take the Laplace transform, and then go from there. Okay, so let's take this y double prime plus y down, and then notice that this is 1 when t is between 0 and pi over 2. Well, generally when you're solving these types of differential equations, you're only solving them for t bigger than or equal to 0. And that's because when we've been using the Laplace transform, we've only been looking at functions that are defined on non-negative real numbers. So that's a restriction of the domain already. So let's notice that we've got our function is just 1 for 0 to pi over 2, so I can just put the number 1 there. You might say, well, I could put the number 1 times the unit step function to say that that number 1 turns on at 0, but like I said, we're only working over positive real numbers in general here anyway. Okay, but then when t flips over to pi over 2, we should have this function flip from 1 to negative 1. But how can we do that? Well, we'll need to turn something on at t equals pi over 2, so that will involve a unit step function shifted by pi over 2. But we need to turn this 1 into a negative 1, so we can do that by subtracting 2. So let's just talk our way through that. So if we plug in anything between 0 and pi over 2, this unit step function will just disappear. But if we plug anything bigger than or equal to pi over 2, this unit step function will give us the number 1, and we'll have 1 minus 2, which is negative 1. So in other words, we have achieved this piecewise defined function with our unit step function, which is really good news because that's exactly what we need to do in order to take the Laplace transform, maybe most efficiently. Okay, great. So now let's take the Laplace transform of both sides of this and see what we get. So for this y double prime, we'll have s squared times capital Y. So we're using our standard notation here that the Laplace transform of little y is equal to capital Y. So we've been using this throughout all of these videos on solving differential equations with Laplace transforms. And then if you recall the formula for the Laplace transform with the second derivative, you should have minus s times the initial value y of 0. So that'll end up giving us minus 2s, and then it'll be plus the initial value of y prime. So it'll be minus negative 1, so that'll be plus 1. So that's our y double prime. Let's maybe be sure that we know that, just since this is the first one of the day. So that orange underline turns into that orange overline. And then finally, we have a plus capital Y from this Y right here. Now we need to take the Laplace transform of this 1 minus 2 unit step function thing. So the Laplace transform of 1 is 1 over s from several days ago. Then the Laplace transform of this will give us minus 2 e to the minus pi over 2 times s over, let's see, s. Great. Because the role of f over here is being played by the constant function 1, and the Laplace transform of the constant function 1 is 1 over s. That's why we get this s in the denominator. Okay, so that's looking good. Now we can maybe move some things around. We'll have something like this, s squared plus 1 times capital Y, factoring the capital Y out of stuff, equals, let's see, 2s plus 1 over s, and then minus 2 e to the minus pi over 2s over s. So we have something like that. Okay, so now we'll divide by s squared plus 1 and we'll have the following object. We'll have 2s plus 1 over s squared plus 1. And then next we'll have 1 over s times s squared plus 1. And then finally minus 2 e to the minus pi over 2s over s times s squared plus 1. Okay. But this s times s squared plus 1 motivates the need for our partial fraction decomposition. So maybe I won't work that out explicitly. We've done that several times already, but what I will point out is that 1 over s times s squared plus 1 decomposes as 1 over s minus 1 over s squared plus 1. I'll let you guys check that if you need to. So inputting that into, let's see, this term right here and this term right here gives us the following. So we'll have capital Y is equal to minus 2 e to the minus pi over 2s over s, and then plus 2 e to the minus pi over 2s over s squared plus 1, and then plus 1 over s, and then plus s over s squared plus 1, and then finally minus 1 over s squared plus 1. And just to be thorough, that's what we get when we take everything from this purple box and input it into this line that's right above. Okay, so now let's bring that capital Y up, and then we'll finish solving this. So this is where we left ourselves off. Now we're ready to take the inverse Laplace transform. So let's point out that that's what we'll do next. So this arrow right here, like I said, is the inverse Laplace transform. So the inverse Laplace transform of capital Y is little y. And now this is going to be some sort of shifted version of the inverse Laplace transform of 1 over s. So in fact, what we get here is minus 2, and then we'll have u to the t, or u evaluated at t minus pi over 2. Okay, so just to reiterate, that's what we get from this bit. Maybe we'll color code these like this. Then what do we have for this next term, which I'll underline in this other purple color? So that's going to be some sort of shifted version of the inverse Laplace transform of 1 over s squared plus 1. The inverse Laplace transform of 1 over s squared plus 1 is something like cosine of t. So in fact, here we'll get plus 2, and then we'll have u of t minus pi over 2, and then we'll have cosine of t minus pi over 2 because of the shifting that occurred. It would have been regular cosine, but we get the shifting from this exponential here. So that's in this purple underline. And then next, this thing which is just all blue underlined will be everything that's not attached to the unit step function. So that'll give us plus 1. This term right here will be cosine of t. This term right here will be minus sine of t. And now let's get to simplifying if we can. And in fact, we can without much difficulty. So I'll use a trig identity to make this cosine of t minus pi over 2 look like something simpler. And in fact, this is equal to the sine of t. Great. Then I can maybe factor out this unit step function thing. That would maybe make it look a little bit simpler. So let's in fact maybe factor out a minus 2 unit step function of t minus pi over 2. And that'll give us 1 minus sine of t when all is said and done. And then we'll have plus 1 plus cos t minus sine t. So that would maybe be one version of the final answer, but it's fairly typical to rewrite these as piecewise functions without the unit step function. And so as a piecewise function, this will be equal to, let's see, 1 plus cosine of t minus sine of t if t is between 0 and pi over 2. That's everything that's not connected to the unit step function, so everything here. And then when you turn on the unit step function, you'll subtract 2 times this stuff from every term. So let's see, you'll have 1 minus 2 times 1. That'll give me minus 1. Then next you'll have negative sine t minus 2 times negative sine t, so that's plus 2 sine t. So that'll give me plus cosine t plus sine t. So the effect had this term change sign and this term change sign. And this is going to be for t bigger than or equal to pi over 2. And this would be maybe a standard way of writing down the solution. Okay, so now that we have this, I'd like to move on to our next discontinuous function that shows up in these types of differential equations. So the next oddity we want to look at is called the Dirac delta distribution, sometimes the Dirac delta function or just the delta function. So we're gonna tread the line between defining this carefully and just playing it kind of fast and loose, which is typical of courses at this level, for better or worse. So for some epsilon, we'll define delta sub epsilon of t by the following piecewise function. So it'll be 1 over epsilon if t is between 0 and epsilon, and it will be 0 otherwise. So we can make a picture of this fairly easily. So you want to think about epsilon as being a pretty small number. I'll expand it out so that it's right there. That makes 1 over epsilon a fairly large number. So this function looks something like this. It's like this little rectangular thing that's going in this manner. And maybe one of the important things here is that the area of this rectangle here is equal to 1. That's because it has area epsilon times 1 over epsilon. Okay, so anyway, now we'll define delta, the delta function, to be the limit as epsilon goes to 0 of delta epsilon. Okay, so now what we'd like to do is see how this delta function interacts with integrals of other functions. And just like we did with the unit step function, this thing is often shifted. Okay, so in fact, what we want to look at is the integral from minus infinity to infinity of f of t times delta of t minus t0 dt. Great. So this is going to be like this object right here, or really the limit of this object right here that's been shifted from the origin to t naught, which is maybe way over here. Okay, so let's write this in terms of our limiting procedure. And like I said, we're going to play this sort of fast and loose, so we won't worry about exchanging the order of limits and integration. So we'll have that this is the limit as epsilon goes to 0 of the integral from minus infinity to infinity of f of t, and then we'll have delta epsilon of t minus t naught dt. And now just to refresh our minds and be super clear about what's going on, let's look at the piecewise definition of delta epsilon of t minus t naught. So this is going to be equal to 1 over epsilon if t is on the interval t naught to t naught plus epsilon, and it's going to be 0 otherwise. So like I said, it moves this rectangular spike to the right or left depending on the value of t naught. Okay, but since it's 0 everywhere except for this closed interval, then that means this integral from minus infinity to infinity will in fact collapse to an integral from t naught to t naught plus epsilon. So this gives us the limit as epsilon goes to 0 of the integral from t naught to t naught plus epsilon of f of t dt times 1 over epsilon. That's because that's the value of our delta epsilon in that region. Okay, great. But now we're going to use something called the MVT for integrals. We won't carefully go over it here, but I will use the result. So MVT for integrals. So by MVT, I mean the mean value theorem. So that says that this integral, well, let's rewrite this. We have the limit as epsilon goes to 0. We have 1 over epsilon. That tells us that this integral, in fact, equals the length of the interval, which is epsilon, times f evaluated at t1, where t1 is something between t0 and t0 plus epsilon. Great. So in other words, the function achieves this like average value somewhere on that interval. But now I think you could probably see where we're going. We can take these two epsilons and cancel them, and we'll be left with the limit as epsilon goes to 0 of f of t1. But where is t1? Well, it's somewhere between t0 and t0 plus epsilon. But if we let epsilon go to 0, it essentially becomes t0. So this gives us f of t0. Okay, great. So let's look at the extreme right and left-hand side of this situation. So the left-hand side of this situation is this integral of this function multiplied by this Dirac delta distribution. And the right-hand side is the value of the function that is associated with the shifting in this delta distribution. So I think that's pretty nice. But now let's look at a quick application of this to writing down the Laplace transform of the Dirac delta distribution. So if we take the Laplace transform of delta of t minus t0, what do we get? So this is going to be the integral from 0 to infinity of delta of t minus t0 times e to the minus st dt. And I guess here, just so that things make sense, let's assume that t0 is bigger than or equal to 0. So if it's bigger than or equal to 0, it's somewhere between 0 and infinity. So that means we can use this rule right here. Because the integral from minus infinity to infinity is the same as the integral from 0 to infinity, because we're capturing this like point where we've moved this spike. Okay, so anyway, we can just apply this rule and evaluate our function, this function right here at t equals t0, and we'll have that this is e to the minus s times t0. That would be the Laplace transform of our Dirac delta distribution. Okay, so let's bring that over here before doing an example or two. So I've gathered what we got on the last board in this second box here. So the Laplace transform of delta of t minus t0 is e to the minus s times t0. Now you might say, well, why would we need to work with these functions? So I think maybe we can kind of most simply describe it for the following reasons. So u is a function that mimics like turning a switch on. So for instance, let's say you're modeling some sort of system that is evolving over time in some sort of consistent way up to a point where something happens, like a switch gets turned on, be that like ecological, or maybe it's an actual switch for like an electrical system. Then you might want to use this unit step function to mathematically turn this switch on. And then delta is like applying a kick to a function. So for instance, if you're like modeling the reverberations of sound waves, so delta would be like hitting a drum one time at a certain exact point in time. Okay, so let's look at our example. We have y double prime plus y equals 1 plus delta of t minus pi. We've got initial conditions, y of 0 equals 1 and y prime of 0 equals -1. So as we've been doing, let's apply the Laplace transform. So that'll give us s squared times capital Y, and then we'll have minus s plus 1. And that comes from this initial condition and this initial condition. Then finally, we'll have plus y from the Laplace transform of little y. And then this equals 1 over s, that's the Laplace transform of 1. And then plus 2 times e to the minus pi s. That's our Laplace transform of this shifted delta function. Okay, so now let's see where we can go from here. We have s squared plus 1 times y can be written as s minus 1 plus 1 over s plus 2 e to the minus pi s Good, like that. Now from here, we'll divide by s squared plus 1. That'll give us capital Y is s over s squared plus 1 minus 1 over s squared plus 1 plus 1 over s times s squared plus 1, and then plus 2 e to the minus pi s over s squared plus 1. So all of this is pretty straightforward in terms of the inverse Laplace transform, except for this middle term right here. And in fact, we'll need a decomposition, a partial fractions decomposition for this middle term right here. So let's write that over to the side. This is in fact equal to 1 over s minus 1 over s squared plus 1. Again, we kind of did that off board, but I'll let you guys check that if you need to. Okay, so let's see what that leaves us with. We'll end up with s over s squared plus 1 minus 2 over s squared plus 1 plus 1 over s. So this minus 1 over s squared plus 1 and that minus 1 over s squared plus 1 combine, and then we'll have plus 2 e to the minus pi s over s squared plus 1. Okay. Now we're ready to apply the inverse Laplace transform. So the inverse Laplace transform of s over s squared plus 1 is cosine of t. So that's cosine of t. This will be minus 2 times sine of t. Then this term right here will be the number 1. So we have plus 1. And then this one will involve some shift. Notice it's related to this term right here. So in fact, we're like going in the opposite direction here, if you will. So that'll give us something like plus 2 times u of t minus pi, and then sine of t minus pi. Great, but now we can apply a trigonometric rule. This sine of t minus pi is the negative sine t, so we can rewrite this as the cosine of t minus 2 times the sine of t plus 1 plus 2 u of t minus pi times the sine of t, well really times minus sine of t, but let's bring that out front. And then you could rewrite this as a piecewise function if you wanted to, but we'll leave it like this. Okay, so I'll leave you with some warm-up problems now. So I've got 2 warm-up problems for you. The first is y double prime minus y equals the following piecewise function. It's e to the 2t when t is between 0 and 2, and 1 when t is bigger than or equal to 2. We've got initial conditions of y of 0 equals 3 and y prime of 0 equals negative 1. And then this last one is y double prime plus 4y equals 8 e to the t plus delta t minus pi over 2. So we have y evaluated at 0 is 8 now, and y prime evaluated at 0 is 0. And that's a good place to stop.